the last week of classes, obviously, so there are only 2 lectures left, today's lecture and Wednesday lecture. Okay, so almost there. Okay, today we will talk about distributed middleware, and then next class we are going to talk about distributed system security. Okay, and then we'll be done. Okay, the exam is next week on the 15th. Okay, we're going to send a detailed email with the room number and the time, so you should already know this, but I'm going to send it out as a reminder. The thing that I did want to say is, as far as the final exam is concerned, typically tends to be comprehensive, but most of the emphasis tends to be on the material after the midterm. Because you are expected to know everything, but more than 3/4 of the questions will be on the part of the class that we covered after the midterm. Okay? So as a strategy, focus on the latter parts of the course, and you should just know some basic things, or just remember some basic things about earlier. Okay? That would be a good way to get prepared for the final. Okay? But today we still have some topics to cover. Today's is going to be on distributed middleware. Okay? I'm going to talk about 4 or 5 different middleware systems, starting from enterprise Java beans, and we'll end with Hadoop and Spark. Maybe we may run out of time at the end, but that's at least the goal for today. Okay. So let's start with distributed middleware. Okay, if you remember, when we were looking at distributed systems architecture back in lecture 2, I talked about middleware-based systems, or at least I mentioned a middleware-based OS, which sits on top of a regular operating system, okay, and gives higher level abstractions to distributed applications. Okay. Today we are going to look at several of these middleware systems that make it much easier to write distributed applications, because a lot of the services that you need inside your application, okay, they are provided by middleware services, so you can directly leverage them instead of having to re-implement your own. Okay. So that's the general idea. So we will look at many middleware systems that use an object-oriented architecture first, and then we'll relax it and look at other types of systems. Okay, so this is our standard.
There is no sound available online.
So I'm going to backtrack again. So today we are going to talk about middleware-based systems. We'll talk about a whole bunch of them. Okay, starting with some object-oriented ones. Okay, so here is an example of a typical client-server system, and you've seen this figure many times already in the context of RPC-based systems. Okay, we remember we have remote procedure calls. There are stubs, which are called proxies and skeletons in the Java world, okay, that are going to essentially relay your RPC methods back and forth. Okay. And then here is the server application. You see that there are some methods and there is some state at the server. Okay. And this is a single application, because there's one server and one client, but in a distributed system like the ones we are going to look at that are built using middleware, there will be many such components on the server, okay, and they will need to communicate or interact with each other. So the question is, how are we going to go about doing that? Okay, so let's start with the first middleware system, which is basically Java based. Okay, this is called Enterprise Java Beans, or EJB. Okay. If you're familiar with Java, okay, and have written code for the lab or for any other reason in Java, you know standard Java. Okay. You can write RMI based application and write client server application with standard Java. Okay. But when you try to build these applications for enterprises or companies, okay, you need a lot more functionality that standard Java does not provide out of the box. Okay? And the enterprise version of Java gives some of these features for us. And the ones that we are going to specifically look at are essentially this notion of a Java bean, which allows us to keep session state, it allows us to save state on disk, all the kinds of things that you have done for your lab, where you have databases, you can have applications communicate to databases, you can keep state on disk. Java provides functionality to make that much easier through the notion of entity beans. Okay? And then Java also provides additional services that allow these enterprise applications to communicate with other components. Okay? So there's one called JMS, which is Java Messaging Service, that allows you to push, publish, subscribe based applications, which we are going to talk about as well today, or send persistent messages to other applications. Then there's one here called JDBC. Okay, so this allows Java applications to easily communicate with databases. Okay, so JDBC is basically the database connector that Java provides to connect to all kinds of databases and so on. Okay. So additional functionality that makes it much easier to write these applications in Java. Okay. And if you go to any company and look at the way they implement applications using Java, they would be using the enterprise version of Java, not the standard version, because some of this functionality will be used for building their application. Okay. With that background, let's look at this in a little more detail. Okay. Let's first talk about what is an enterprise Java application consists of. At its core, enterprise Java application look like any other Java application. Okay. So it's object oriented. Okay. You have classes, they have methods. Okay. You have to declare the interface that your objects are going to export. Okay. These applications are built for remote communication, so all of them are RMI based. Okay. They are not standard single machine applications. So all of them are going to export some interfaces that can be accessed by clients or other server components. So you essentially have an interface that you export, okay, and then you have the actual code that you implements that interface, which is basically your remote interface. Okay. Now there are many interesting additional details that you can have in enterprise Java applications. One of this is called persistent objects. Okay. You can take an object that you instantiated, okay, in a Java application. Okay. You can write it to disk. Okay. You can restart the application and recreate it. Okay. So this allows your code to keep its state across server reboots or application restarts. Okay. Typically in your Java code, your state, your classes are all in memory. If your code essentially stops and then you restart your program, all of that state is lost. Okay. In this case, you can persist the state to disk. Right? And you will use similar things like serialize and deserialize, which we had encountered when we were talking about essentially passing parameters and marshalling and demarshalling of arguments. The same functionality is used to persist the state on disk and recreate the object. Okay, so you can take an object, write it out to disk, okay, stop the application, restart it, read back all of your old object, and you're now back to where you were. Okay. So you have these types of functionality which essentially allows you to have persistent objects and things like that. Okay, so we'll look at this in more detail now. Okay, so in the enterprise Java world, you should think of there are 4 types of objects. Okay, you can have essentially what are called stateless objects, what are called stateless session beans. Okay, so these are standard applications, standard classes that when you instantiate just look like Java classes. They don't have any state, so there's nothing to save or recreate or anything like that. Okay, and then there are things called stateful session beans. So these have 2 attributes that are important. First, there's the notion of a session. Okay? Just as in the web application, the browser has an ongoing session with the server. In the Java world as well, when 2 components interact or a client component interacts with the server, you can create a session. Okay? And then you can send requests, and that session state is stored on the server side, so you don't have to keep sending information that you sent before. So if you want to build, let's say, an e-commerce application, okay, the shopping cart that you have is essentially the state of that session. You may have taken an object and put it into a shopping cart. That session state. Okay, you can essentially keep that session state on the server side using these types of objects. Okay, they are called stateful session beans. Okay. And then you have entity beans, which, as I was saying, are persistent version of this. Not only do they have state, okay, you want to preserve the state across invocations of the program, across server reboots and so on. So you want to make sure that the state is actually saved to disk, so that you can recreate that state at some later time. So it's no longer just state is saved in main memory, it's persistent to disk. These are called enterprise beans. So these are the newer type of objects that you will not see in standard Java application, at least not out of the box. Okay? And then there are message-driven objects which are designed for messaging. Okay? They allow you to not just send RMI type messages back and forth. You can send a message that will be persisted in some location, and the recipient of that message can come back at a later time and pick up that message. Very similar to how you send email. Okay? When you send an email, the mail that you send goes and sits in somebody's mail folder until they are ready to receive it. It doesn't disappear because the other party is not checking email at that particular instant in time. Right? So you have these message-driven beans as well. So 4 new types of classes that you have to think about in addition to standard Java classes. Okay? So that's EJBs in a nutshell. I'm going to build on this background and talk about another middleware system that takes all of these ideas and shows you some additional functionality, and that's called CORBA. Okay? CORBA is an acronym that stands for Common Object Request Broker Architecture. Okay? Don't need to really remember the acronym, but the thing you do need to remember is that at the heart of this middleware is an entity called the Object Request Broker, or an ORB. Okay? And as you can see, the ORB essentially is a horizontal layer that allows all other components in your middleware to communicate. It's the layer that enables inter-object communication. Okay? So ORB is essentially the core of the middleware platform. It handles communication between objects in the server. On the server side, it also enables communication between the clients and the server, and it essentially allows all of these things to work together well. Okay? Now, on top of the ORB, you will see that there are all kinds of services in CORBA. Okay? And I have a list actually on the next slide that shows you these services. And what you will see is CORBA is a very heavyweight middleware system. Okay? In some sense, the designers of CORBA thought about what is it that you developers could possibly want when they're developing a distributed application. And anything they could think of could be a functionality that a developer desires. They made it into a service. Okay? And you will see they're called horizontal services, vertical services. Vertical means they're domain specific, horizontal means they're general purpose. For this class, we'll not distinguish between them, we'll just think of them as services. And here's a list. Okay? We'll not go into every single line here, but this is just to show you that a lot of things that you have to implement typically, they made it into a service. And so there is a concurrency service. If you want things like thread pools and thread pool management, you go to the concurrency service. You don't need to write your own code. Okay? You want to build transactions in your system, there's a transactional service. So you can just begin transaction and transaction, that service will give you atomicity guarantees. Okay? You want to essentially send some notifications, there's a notification service. You can just use that service will deliver your notification to whoever it is that you need to notify. You want to persist your objects, similar to enterprise Java beans, as a persistent service. You can just ask that persistent service, say these are objects whose state need to be persistent. Okay? So you will see practically anything you could think of, there is essentially a type of a service that was built for that functionality. Okay? So the designers of CORBA thought that this will make it much easier to write distributed application, because a lot of functionality that you typically want in your application is already abstracted out as a service. You can think of services as libraries at some level. Okay? And so you just use that functionality and you get that functionality without having to write code for it. Okay? So, or that was their thinking. Okay? Now it turns out that even though CORBA designers went to great length trying to come up with a lot of these services, CORBA actually never took off, okay, as a platform that was widely used to write distributed application. And the main reason it did not take off was the middleware platform became extremely heavyweight. Okay? The overhead, the learning curve in knowing about all of these and using them, okay, was so high that it did not make sense to use CORBA for simpler distributed application. Okay? And you have to really work hard to get past that learning curve, so it only makes sense to use it for large-scale applications where many of these services are giving you a lot of benefit without having to write your own. Okay? And that's never a good design strategy. Okay? You want your system to be used as widely as possible. That is how it becomes successful. You don't design it so that only a small subset of you developers think it's useful and everybody else says that's too hard to learn, let's just try to use something simpler. Okay? As a result, never really took off, okay? But some aspects of it still live on even today. Okay? So an example of where Corba-like functionality is used even today is in the Linux operating system. If you're familiar with Linux, you will know that there are two types of desktop managers, if you will. One is called GNOME and the other is called KDE. GNOME is actually based on Corba, a stripped down version of Corba. Okay? It uses Corba-like functionality for communication between objects and so on. Okay? That's really the only widespread use that you can still see today. Otherwise, this middleware actually is not as used in commercial world and so on. Enterprise Java being very widely used. Okay? It is not this heavyweight. As you can see, they had a few things that they thought were very useful to provide for application developers, and they did them well. Corba developers said, let's try to put every service we can think of into the middleware. Did not work as well, made it too heavyweight, overhead was too high. Okay? Be that as it may, okay, still a good use case and to think about what all they did, how some of those ideas live on in other systems even today. Okay? So this is the object model of Corba. Okay? And you see this looks no different from any other the Enterprise Java one or any of the RMI ones. You still have an RMI based or RPC based architecture, except that instead of a stub you have the orb sitting there, okay, that's responsible for communication. Okay? Corba had all kinds of interesting functionality where you could have dynamic classes or dynamic objects. These are classes that you did not know about when you wrote your code. Okay? You could still import the interface of these classes at runtime, get to know the methods and call, make invocations on those objects. Okay? Typically, that's not how you will write code. When you write code, you need to know what is the object you're interacting with, what methods it, RMI methods invokes, and you write those in your code. In this case, you can do that dynamically on the fly. This allows you to interact with newer features that was not thought of at, let's say, design time. Okay? So all kinds of additional functionality, but at its core, still an RPC or an RMI based model. It looks no different from any of the others. So there are objects, you invoke methods on objects. Okay? Now, if you remember when we were talking about RPCs, okay, I introduced different RPC models. Yeah, I said the default is synchronous, you can have asynchronous, you can have one way, you can have deferred synchronous. Okay. All of those ideas originated from here. Okay. So Corba was essentially the first middleware that says, why just provide synchronous RPCs? Let's provide in the RPC model every possible way any developer might want to use that RPC. So they had synchronous, okay, which is the default one. Okay, they had asynchronous, which they implemented as one-way RPCs. They had deferred synchronous and so on. Okay. They also had all of those failure semantics where you could say, if your response comes back, what is it that you can say about the RPC call? So most of them had at most one semantics, but for one way it was best effort. Okay? So those ideas that we had talked about in maybe lecture 3 or 4, they actually originated here. Okay? But they live on in other forms in other RPC systems. gRPC has some of these ideas as well, as you may remember when we talked about gRPCs. Okay? So those are object invocation models. Okay? And then the other thing in Corba that was actually very useful, that is now become its own way of writing distributed application, is the notion of publish subscribe. Okay? This is called PubSub. Okay? So PubSub is now a popular way to write distributed applications. So let's spend a few minutes talking about what is PubSub, and we'll see that again Corba supported this as well. Okay? So the idea here is you can think of, rather than thinking of your application as clients and servers, okay, you can think of your applications as having components, and components are either a producer or a consumer. Okay? Producers produce data or events, consumers consume data or events. That's how you should think of writing your application in a PubSub world. Okay? And the way this works is the consumers can subscribe to certain types of data or events. Okay? And publishers just publish event. They don't actually send messages to specific components. Okay? So in socket world or RPC world, you are making RPC calls of a certain process, or you're sending a message over a socket to a certain recipient. That's not how PubSub works. You just publish some data, okay? And when you publish data as a publisher, you don't actually address it to any specific component in the middle entity called an event channel. And the event channel then figures out which components, which consumers to deliver that data to, if any. Okay? So what consumers have to do is they have to register themselves with this event channel and specify what types of events they want to subscribe to. Okay? And then the event channel will keep track of those subscriptions. And whenever a new event is published by the producer, which is also called in this case a supplier, okay, you will check saying, is there a subscription that actually matches this event type? If so, you will deliver to every consumer that has subscribed to that event type. Okay? So your event channel is essentially, think of it as a buffer that sits between the producers and the consumers. Producers are generating data and putting it in the buffer. Okay? And then the event channel tries to figure out of all the buffer data, who all should be sent, who all should receive this data. Yeah, those are your consumers. Okay? So that's your basic idea of a publish-subscribe paradigm. Okay? So it's different from everything we have studied, which is it's not like an RPC, it's not like socket communication, where you're explicitly sending requests or messages to specific components. Here you publish data without a specific recipient that the publisher will specify. The recipient will be determined by the event channel. Some events may have no recipients at all. No consumers have subscribed to that event. So it will sit there and after a while it will be deleted from the buffer. Okay? Others might have this for, they are subscribed to that event. So the same event may be supplied to many consumers. Okay? So there can be all kinds of ways data flows from producers to consumers. Okay? That said, now the question is, how is the event channel actually implemented? And you will see that there are two models to do this, a push-based model and a pull-based model. Okay? What is shown in this picture is a push-based model, where the producers publish or push data into the event channel. So you publish and you put it into the shared buffer, and then the event channel looks at the subscriptions and then pushes data to consumers. Okay? So this is push from the publisher to the event channel and push from the event channel to the consumer. Okay? The opposite model is also true, which is essentially a pull-based model, which is shown in this picture. Same publish-subscribe application, but the event channel is implemented using a pull model. Okay? So in this case, the event channel is pulling data from producers. Okay? And then the consumer, so the data will come and sit in a buffer area, and it's the job of the consumers to pull data from the event channel. Okay? So this is a pull-pull model. Okay? And you can have hybrid models as well, where you can have push between the producer and the event channel, but you can have pull between the consumer and the event channel. So you can do push, pull, pull, push, all four combinations are possible, but the simpler one is push, push, or pull, pull. Okay? We will look at this in a little more detail here. Okay? So here is two ways you can implement the pull-based model. Okay? So here is essentially you can use an asynchronous callback, or you can use a polling-based method to actually ask. Okay? So in an asynchronous callback, what happens is the consumer, or the client application, is going to register itself to the event channel and say, if your data, make a callback, and then there's going to be a notification saying there's some data, at which point you'll go and pull that data from the consumer, from the event channel. Okay? This is a callback model where you ask to be notified when there is data to be pulled. So you will basically not sit there and keep polling, you will just be told when there is data, and then you can go and pull that. Okay? That's an asynchronous callback model. The other one is our more standard polling-based model, which we have looked at in context of caching and many other scenarios, where the client application, in this case the consumer, is polling the event channel saying, do you have any new data that matches these attributes of the subscription, and if so, you will get that data, otherwise you will just wait for some time and poll again. Okay, so you can use either of these two mechanisms to implement your pull based. Okay, the push is much simpler because you just wait, and then the event channel is just going to send you some data whenever it has any data to push. Is this clear? Okay. So the notion of publish subscribe, okay, also originated in Corba, okay, but that has lived on. Okay. And there are lots of publish subscribe system that you can find today. There are many of them are open source system. There's one called Apache Kafka, which is very popular to write distributed applications, open source system. All of them use this architecture, okay, but the Corba version of it, of course, doesn't live on because Corba itself has not actually taken. But again, another of those ideas that were good is they put them in the Corba middleware thinking. Why just stop at RMIs or RPCs? Let's also support push, publish, subscribe applications in this middleware on top of it. So that is where all the event channel came in. Any questions here? Okay. So we are going to switch gear, talk about a different middleware system. This is middleware system in the Microsoft or the Windows world. Okay. The EJB's cross-platform, because it's Java-based. Any OS platform that runs Java can run EJB. Okay. Corba was designed largely for Unix-based systems, ran on some versions of Windows, but was largely Unix-based systems. And there was, of course, middleware systems that came out of the Windows world that were designed by Microsoft. Okay. And so there were a whole slew of them. Okay. The first one was called COM, which was essentially component object model. Then there was one called DCOM, which was distributed component object model. It evolved, and we'll see the evolution as well. And finally, today we ended up with .NET. Okay? So you have Microsoft as a .NET platform that allows you to write distributed application. At some level, .NET doesn't look very different from gRPC philosophy, which says that you can write different components in different programming languages and they can still communicate. Okay, remember, gRPC is language independent and platform independent. Okay? You can write code, client and server in two different languages and they can still communicate over RPC. Same is true in .NET. Doesn't require you to use just one language like C#. You can write components in different languages. There is language independent, so you can still have communication. But before we get to .NET, let's look at a little bit of the history here. Okay? So the lowest layer, the oldest layer, sort of version where Microsoft Windows started supporting things like RPCs was called the COM layer. Okay? So COM was essentially the ability to make very simple RMI calls. Okay? So it was not very different from what you already know. Okay? And then what happened is, because Microsoft Office was the biggest application suite that was popular on Windows, okay, they essentially tailored COM to support Office applications. Okay? What does that mean? Okay? So if you think about, let's say, a PowerPoint file that you create, you can embed Excel charts into PowerPoint. Okay? You can make an Excel chart. Okay? You write some data in Excel and you can turn that into a bar graph and you can embed that into PowerPoint, and if you open that PowerPoint file, you can directly edit that Excel chart without having to go open Excel. Okay? If you've done any presentations where you embedded charts, you'll know exactly what I'm talking about. And same is true, you can make a figure in PowerPoint and you can put that PowerPoint figure directly into Microsoft Word. Okay? So to enable this functionality where data from one application can be embedded into another application, okay? Or you have one document that actually embeds objects belonging to some other document type, they essentially build something called OLE. Okay? This is called object linking and embedding. Okay? The whole purpose of this OLE layer was to use RPCs for Word and PowerPoint and Excel to communicate with one another. Okay? And the reason they want to communicate is you are creating, as a user, more complex documents where you're embedding one document type into another. You're embedding Excel into PowerPoint, or embedding PowerPoint into Word. Okay? And when you double click on some object, Word has to then communicate with PowerPoint in the back end, so you can edit that figure directly in Word. Or if you do that in PowerPoint, you want to edit your chart, you don't have to go open Excel. Excel opens within the PowerPoint context, but this needs this application to communicate. Okay? And the way they are going to communicate is using RPCs or RMI-like features. So that was essentially the COM layer, but they added this document linking and embedding layer on top of it. Okay? That was essentially their OLE layer. Okay? And then this was basically in the 90s. Then basically you had the World Wide Web. So then this we basically said, why not allow some of this functionality in web documents as well, okay? Where you can essentially have web documents with other types of documents communicating with one another and scripting at the server side. That gave rise to the ActiveX layer. Okay? If you know Microsoft browsers, they used to support this ActiveX layer that allowed you to build richer web pages and whatnot. Okay? So that's been the evolution, and eventually you had DCOM and then you have .NET. Okay? So that's the history here. Okay? So essentially you had the old days, you just had a very simple RMI layer, then you had an OLE layer that sat on top that allowed Office applications to communicate using COM. Okay? Then ActiveX was OLE plus few new features designed to support web documents. Okay? And DCOM was essentially all of those, but now across machines. Okay? Because if you think about it, OLE is still single machine where Office and Word, Office, all the Office applications are still on the same machine. You are doing RPC, but they're RPC on the local host, okay? Not across machine. This made it distributed. You can essentially go across machines. And .NET was just a new version of DCOM that said, let's make it language independent. You don't have to write everything in the same language. You can write some components in one programming language, some other components in another, and so on. Okay? So that's basically the history. Okay? And I'm going to now go into some details so you now get some understanding of what's going on. Okay? At its core, DCOM doesn't look very different from Corba's object model or the Java's enterprise Java Beans model. Okay? The DCOM is not as heavyweight as Corba. Okay? Corba had way too much functionality that was embedded in this. Okay? DCOM looks more like enterprise Java. And it has certain types of objects that are useful for developers. So you can have persistent objects, you have the ability to dynamically create objects on the fly and so on. And you will see that the picture is the same as what we've seen before. Okay, there are proxies and stubs at both sides that are essentially allowing you to do RMI communication. Okay? So all of these use the same basic architecture. Okay? But they are tailoring this RMI based functionality to build higher level middleware services. Okay? So it looks different from what you've seen, and there are some interesting things here. Okay? So just as you had enterprise Java Beans, it has persistent objects. Okay? In the DCOM world, you had something called a moniker, which was their version of persistent object. Okay? You could take a object in a Windows application, you could write it out to disk, you restart the application, you read it from disk, all your state of the object comes back. Okay? Whatever data was in the object variables, all of them come back exactly the way they are. So you had essentially a way to create persistent objects. You could also have objects leading to URLs. They provided all kinds of additional functionality as well. Okay? And by default, objects are not persistent, no different from when you write your Java code. Okay? You instantiate an object, you close your application down and restart it, you don't expect the old object to come back. Okay? So objects by default are always transient. Okay? But when you make them persistent, then the middleware is going to save its state for you so that when you restart it, you can recreate that object as it was in the previous invocation of your program. Okay? So that's kind of functionality that you want if you want to have long-running applications that keep state and so on. Okay? The other way to do this, of course, is to put everything into a database. Okay? Your state is in the database, so the memory you don't keep state. Okay? That's the web way of writing application. Okay? You don't actually keep state in memory, okay? Or you don't write object state to disk, you put the state in your database and you just interact with the database. Okay? But here you could actually not have a database at all. All of that state that you would normally keep in files and so on, you can make it part of the object state, but you persist it on disk. Okay? That's another way of writing these applications. Any questions here? Yes.
What does object being persistent in terms of Windows here mean? Like we know the Java objects, so what are window objects?
Oh, what are Windows objects? Oh, maybe I should have said. It's Microsoft Windows OS. This is basically DCOM is a middleware that is designed for the Windows platform. Okay? That's all it means. So basically, it will not run on Macs or Linux by default. It's basically only going to run on Windows servers or Windows desktops. Okay. So that's a very quick run through of different object-oriented middleware systems. Okay. Now we are going to switch gears and start talking about other types of middleware systems that are used for other use cases. Okay. The first one, okay, and then we'll talk about distributed data processing next. The first one is for distributed coordination. Okay. And the idea here is that you need different ways for application components or server components to communicate with one another. Okay. And the ones that we have assumed is actually, so far when we talk about object-oriented platforms and so on, is just one of many different possibilities. So let's first talk about what kinds of coordination you can have, and then we'll look at ways you can achieve this coordination. Okay. So the idea here is to separate the computation from the coordination. Okay. In object-oriented world, the both are actually tied very intimately to one another. Okay. But you can decouple them, which gives us other types of middleware systems as well. Okay. So let's go through them, and then you'll understand what we mean by coordination. Okay. So direct coordination essentially means that the two interacting components, they are both executing at the same time, and they're interacting using RPCs or socket communication. Okay. Both have to be running maybe on different machines, and they interact. That's called direct coordination. Okay. So this is how in the physical world, think this is almost like text messaging. Okay. Or you use iMessage or whatever your messaging platform is. You and your friends, they are basically, you are interacting with one another. Both of you are actually there communicating with each other. Okay. That is direct coordination. Okay. Mailbox-based coordination is one where you send a message, okay, but you don't expect the other end to process that message immediately, but expect that it will take some arbitrary amount of time to be processed. Email is a good example in the physical world. Okay. Unlike text messaging, if you send an email, you don't expect a reply to come back in a few seconds. It may take hours, days for somebody to even read that message, and then they might respond. Okay. So now you have made the communication weaker because both parties that are part of the communication are not active at the same time like they were in direct coordination. So email, so this is direct coordination is like text messaging, mailbox coordination is more like sending email. Okay? Now this is the reason this is called mailbox coordination is they basically have an abstraction called a mailbox, which looks similar to an inbox, where messages go and sit, and then you can take delivery from that mailbox at a later time. Okay? Looks like an event channel, okay? Except that the event channel is persistent on disk. Okay? Just as your mail lives on disk, it does not live in memory. Okay? That's mailbox-based coordination. Okay? Third type of coordination is meeting room coordination. Okay? So this is more like publish subscribe. Okay? So maybe you essentially announce a meeting, you put it on the event calendar, okay, saying there's going to be a talk, some speaker is going to come and talk about this topic. Okay? Now you posted this, you did not address that to anyone in particular, and moreover you don't know who's actually going to come to the talk. Okay? So some users who find interest in the topic will show up. Okay? So now you are communicating using an events calendar to a broad group of users, and that message is not addressed to anyone in particular. Anyone who's interested is going to show up at that time. Okay? So this is meeting room coordination. Okay? So you can just call a meeting saying, we are going to have a meeting on this topic, anyone who's interested should come. Okay? And the last one is called generative, where messages are neither sent to anyone in particular, not at any particular time. And we'll talk about that in more detail. Okay? But if you think about these four types of coordination, you can classify them in this table as is shown, and there are two axes to this table, okay? Space and time. Okay? And what that means is, are you coupled in space when you communicate, and are you coupled in time when you communicate? Okay? So the direct coordination means you are both coupled in space and time, which means that you ought to be talking to one another at the same time, and messages are being explicitly addressed back and forth. That means you're coupled in space. I'm sending explicit messages to a server or to another user, to text messaging, they are sending me back. Okay? So that's direct coordination. Okay? Mailbox-based coordination is coupled in the spatial dimension, which means the messages are addressed to someone, okay? But they are not coupled in time, which means the other party does not have to respond to me or process that message immediately. Okay? So it's uncoupled in temporal dimension. Okay? So the other party can look at that message at a later time. Unlike text messaging, where messages are being addressed to specific parties, and you are getting messages, responses back at the same time. So you are actually coupled in both space and time. Okay? Meeting oriented says that you are coupled in time because you called a meeting at a certain time, but the announcement of the meeting was not addressed to anyone in particular, so it's uncoupled in space. Okay? And then where you are uncoupled both in the temporal and the spatial dimension. You are sending messages that are not addressed to anyone in particular, and those messages may or may not be read by any other party down the road. Okay? So that's the most loosely coupled form of communication. Okay? We looked at these other examples, or at least you know of these other examples using physical world examples like email or text messaging or RPCs, but this one we have not looked at so far in this one. Okay, so this is the one we look at. Okay? It's also called shared Google space model, which we will see in the next slide. Okay? So, yes, question.
When applications are coupled in time, how does clock synchronization work in that case then?
Okay. Question is, if applications are coupled in time, how does clock synchronization work? So coupled in time does not necessarily mean that the clocks have to be synchronized. It just means that both parties have to be active. Both, either the parties could be two people who are sending text messages, or they could be two processes that are sending socket messages back and forth. Both of those have to be active at the same time. Okay? That means if I send a message, if a client sends a message to the server has to be executing. If it's not executing, the message is not going to reach it. Okay? So at least think of it as if you're coupled in time, both processes are actually executing at that time, at that instant, where that message is going back and forth. That's what it is. In the mailbox case, you send a message, the other application does not have to be executed. Okay? This is like the other users' mail application does not have to be running. They can start their mail later and then take delivery. So that's what it means. Okay? All right. So let's talk about generative communication. We are going to look at it through the lens of a specific middleware system called Genie, which is a Java-based middleware system. But the ideas are actually general enough that they apply to many other systems. Okay? First thing is, okay, what does this model look like? So think this, the best way to understand generative communication is a bulletin board model. Okay? A bulletin board is the best example of a physical world that maps to generative communication and are decoupled in space and time. Okay? And here's the standard example that I always give. Let's say that you are graduating, okay, and you have some furniture that you want to sell before you move somewhere else. Okay? What is it that you are going to do? You will make a flyer, okay, and you will go to some bulletin boards and you will post this flyer. Okay? And you will say, I'm selling my sofa, or I'm selling my couch. If you're interested, call me, and you will have your maybe a phone number that's attached to it that you can someone can just take and call you at a later time. Okay? So if you think about this mode of communication, what have we just done? The first thing is, when you posted this flyer, it's not addressed to any specific person in particular. You just put it up saying anyone who's interested can come and look for this information and then contact you at a later time. Right? So you did not expect the other person to be waiting there, waiting for your message. You just went and posted it. Someone can come at some later time and take delivery of your message and contact you. So it's decoupled in time, right? And also decoupled in space because you didn't address it to anyone in particular. Unlike sending a USPS letter, you put somebody's name on it, so that letter is actually addressed to someone. Okay? It's not going to some arbitrary other people, it only goes to the intended recipient. Okay? But a flyer that you post on a bulletin board can be addressed, not addressed to anyone in particular. Okay? This is the same concept here in a distributed systems world. Okay? Application components are going to communicate using a shared bulletin board. Okay? They are going to post messages like flyers that's not addressed to any particular other component at all. Okay? And those messages will sit on the bulletin board, and other entities can then come and look for matching messages and take delivery. Okay? So that same idea applies here. But then you can think, what is a use case for this? Where would you ever use something like this? Okay? This also happens that it has many interesting use cases. One is called zero configuration systems. Right? So I'll give another example where I'll make it clear, which is, let's say you go into some new Wi-Fi environment. You go to someone's house or you go to some new organization, you connect to their Wi-Fi. Okay? So now you are on a new network, you know nothing about that network, you just connected to it. And let's say you want to print something. Okay? Now if you want to print something in some new environment, you need to know, is there a printer in that environment, what its address and whatnot, you have to configure it, and then you can print. Okay? Lot of manual work. Okay? Now you can say, what if that new environment had a bulletin board, okay? And all the printers in that environment had posted their information on this bulletin board saying, I am a printer service, this is my IP address, okay? And this is the printer model or whatever it is. So all then that you have to do in this case, your machine, not you as a user, has to do is you go into a new environment, okay? You just go to this bulletin board and say, what services are available in this environment. You'll say, okay, here's a print service. Okay? So if my user needs to print, I can just go query for a print service and I'll find a note saying I'm a print service. I just find the information, I contact the printer, I print. Okay? User doesn't have to do anything because the printer is automatically discovered by your machine. Okay? And then you will essentially configure that printer based on the information there and print. Okay? So this makes it much easier where there is less user involvement in discovering new services or hardware that's present and using that hardware. Okay? The only way you could do this is if these services are advertising themselves. Okay? You can advertise yourself using a bulletin board. That is precisely what a bulletin board is. You post flyers to advertise something. Okay? That's one way of advertising. Of course, there's another way of advertising, which is broadcast messages. Some networks actually use that where they don't use a bulletin board. Periodically, any service that needs to advertise itself is going to send a broadcast packet that reaches every other machine on the network. In that case, you just wait and listen. Okay? And then suddenly you will discover new services. So there are two ways to do this. One is flood the network. So it's like you go around shouting saying I'm a print service, and then somebody who's listening to you will say, okay, I need this service. So that's your broadcast. The other is you put a note on your bulletin board and you get the latter. Okay? Now it so happens that if you use a Mac, okay, you will see that there are all kinds of shared services your Mac seems to discover, like shared iTunes libraries and all kinds of things. Okay? That is actually done not using a bulletin, that's using zero configuration, but it uses a broadcast-based approach. Okay? There is no bulletin board in that case. Okay? There's a service that Apple has, it's called Bonjour. Okay? So essentially these services just send hello messages to everyone else and advertise them. Okay? But this is more efficient because you're not sending messages all the time over the network. Okay? So that's an example of how you will use bulletin board services. Right? Now we'll see how to implement a bulletin board, and then you can think about how to write applications on top of this. Any questions on this? Okay. So here is the basic idea. Okay? So it's going to use a publish-subscribe model. Okay? In some sense, publishers are the ones that are posting. So this thing in the middle is your shared bulletin board. Okay? Publishers are going to post the equivalent of messages or flyers to this bulletin board. Okay? Consumers are going to come to this bulletin board and query for specific types of things they are looking for. Either a type of data, type of service that you want to discover. You just send a query, and then whatever matches comes back to you. Okay? And then you can essentially use that information to do whatever you want. Okay? That's the basic idea. Okay? So it's going to use publish subscribe. I already told you what publish subscribe is. So now let's look at how are you going to implement this bulletin board architecture. Okay? Now this is going to be different from an event channel, okay? Because in event channel messages don't persist. Okay? The previous version of publish subscribe that I talked to you, which had an event channel, that was a memory buffer. Okay? Data did not persist. You publish some event, you deliver it. If you don't find any matches, then you throw it away. It's not going to sit there. As opposed to a bulletin board where messages may persist for long periods of time. So this has to be persisted on disk as well. Okay? Can't just be an in-memory buffer that you have all of this data. Okay? So this is implemented using actually it's a database, but in Genie world it's called a Java space. Okay? So Java space is basically a database, and then you can essentially do read or write operations or get or put operations on this Java space. Okay? So here is a process that's going to write data item A. This could be a new flyer or a new service you advertise, and that one writes B, and this one is going to essentially look for all tuples that match a certain value, which is like a query that you do on a database, and it happens to match C. So you can do one of two things, just read C and leave C there for other users, or if you are the intended recipient, you can remove it from the database. You can remove it as well. So you can do both in this case. You will see that in this case you will return C and you can optionally remove it. Okay? Yes, question?
You said that none of the, like all the messages that are put into this shared bulletin board are not intended for anyone. Then how will C know that it was, you just said that if it was intended for it, can decide to remove it or not. If
Right.
there's no intended recipient, then how is it?
That's a good question. The question is, since I said that messages are not intended for any one process, how does this process that just read C know that it's essentially has to delete C from the database? Okay? That depends on whether the messages you are inserting have one recipient or many recipients. You don't need to name the recipient ahead of time. Okay? But if it's just one recipient, then the first time a recipient comes along and looks for C, you can delete C. But if it's many recipients, then you don't remove. So maybe it's like, if you think about it, you can think of examples in the real world where you might be trying to find a lab partner. Okay? So you say, I want a lab partner. Somebody comes along, say, I want to be a lab partner. You're done. You don't need to keep that message there because the message is being used and you found whatever you're looking for. Or maybe you're selling 10 pieces of furniture. In this case, just because one person came and looked at the message doesn't mean you remove it, because they may only want one of your furniture. You keep it for one. So it depends on what it is that you're trying to do. Java Space gives you both of those functionality. Okay? All right. So essentially that's how Java Spaces work. So you are going to write to this bulletin board. You can then remove it. You can also ask for asynchronous notification, so you don't have to keep polling. Maybe you're looking for furniture. You don't have to keep going every 6 hours to the bulletin board saying, has somebody put a flyer? Is there any furniture available? You can just ask for the Java Space saying, I am looking for messages that match these attributes. If a new message comes, notify me. And then I'm going to send my query rather than periodically polling. You can ask for asynchronous callback, so you will then get a notification, and then you go poll. So this is another way you can actually have the Java Space notify you. Okay? And here is the actual implementation of it. So essentially it's a replicated database. Okay? And so you will see that there are many copies of your replicated database. Okay? And so the way you can do this is one of two ways, where when you try to write to the database, okay, you can either write to your local database, or you can replicate that right across all databases. And depending on which of the two you pick, the reads are going to work in the opposite way. Okay? The way you want to think about it is, let's say if you think about a physical bulletin board, let's say there's one on every floor of this building. Okay? So you have to assume that either every message is posted on all bulletin boards, in which case if I need to look for a message, I just go for a local to my local bulletin board and see if there's a matching message. Okay? Or you put flyers on any one board, okay? And then if I'm looking for something, I have to go ask all boards saying, is there a matching message? Okay? Same is true here. If writes are replicated, means writes are put on all replicas of my database, then reads are local, because every flyer has been put everywhere. So I can just go to my local tuple space or Java space and just say, is there a matching message? Okay? So if writes are broadcast, reads are local. Okay? But if writes are local, which means I just go and post that on my local bulletin board, reads have to be broadcast. If you're looking for something, you ask everyone, say, is there a message? Okay? So those are the scenarios that are essentially shown here on this slide and this other slide, but basically you can have either architecture, doesn't really matter. Okay? That depends on whether you're replicated bulletin boards or partition bulletin boards, where each of them have different messages. Okay? In either case, you are using a database, an underlying database, which we call a Java space, to implement this notion of a bulletin board architecture. And on top of that sits a pub sub system that allows entities to communicate with one another. Okay, so you combine publish subscribe with a persistent database so that messages can live for long periods of time. You can go query them later and so on. Okay, is this clear? Okay, so last 10 minutes I'm going to talk about other types of middleware systems. Some of this you may have encountered in other courses if you've taken, let's say, systems for data science or something like that, you may have seen Hadoop and Spark and whatnot. But I do want to introduce this briefly so that you at least know what these types of distributed middleware systems are. So these are middleware systems that are designed for large-scale data processing, not communication. Okay? Everything we talked about was some form of communication, but you can have other types of systems that are basically designed for other needs. These two systems we'll talk about: Hadoop, which is MapReduce, okay, and then Spark. They are for large-scale data processing. Okay? And you all actually have knowledge of why you need to process large-scale data sets. Okay? There are all kinds of scientific data sets that are out there that you might need to process. The data sets are very, very large, which means you cannot run your the process that processes them on one machine. You run them on a cluster. Okay? So each process is going to read some part of that data, do some processing, produce some intermediate results, and so on. Okay? So there are all kinds of use cases for this big, what's called big data processing. Okay? You can have financial data, you can have health data, you can have genomic data, image data, and so on. These are all medical data of brains and whatnot. Okay? And in today's world, you can think of machine learning training being the canonical example of big data processing. Large data set, you want to train a model. Okay? Of course, you may have to do other things. In this case, you are not necessarily training models. You are processing the data, in this case, maybe to find CT scans or MRIs that show you signs of tumor or all kinds of other things. Okay? So there is various data processing needs, but the common thing here is the data set is large, okay? And you need to process it to produce some end result. Okay? What are ways to go about doing this? Okay? So there are a few things. First is you got to parallelize your data processing. Okay? You can't run this job on one machine. It's going to take a very long time. Okay? You want to parallelize it. Okay? You can use CPUs or you can use GPUs. That's an orthogonal point, but you need more than one machine to process your jobs. Okay? That's the first thing. Now in the MapReduce model, the way you are going to do this processing occurs in two stages. Okay? There's a map stage and a reduce stage. Okay? I'm going to give you a very quick example of what MapReduce means and then what the shuffle stage is. And so this picture shows you three machines. Okay? Each of them has essentially some data being processed, and first all the machines do what is called the first stage of the processing, which is called the map stage. Then they exchange data, which is shown by this black arrow. Then they perform the second stage of the processing, which is called the reduce stage. Okay? Now, a very simple way to understand this is, let's say you are given a large data set and you want to sort it. Okay? You all know what sorting does, right? Basically, there's a key on each data item, you want to sort it. Okay? So what are you going to do? How are you going to sort it? So in the map stage, each of these machines will read some part of the data set. Okay? Because you have a large file, okay? You will say this machine reads the first n elements, and then the next machine reads the n elements, and so on and so on. So you read it, okay? Then you can essentially look at the data that you just read, and you will look at the key. Okay? And what you can do is, because you want to sort this, you can say the first machine, the second stage, you want all keys from, let's say, A to D to be sent to the first machine for sorting. And then the next one is going to take all keys from E through some value, go to the next machine, and so on. So each machine now has some elements that they just have to sort locally, and then you can get the whole sorted file. Okay? So what will happen in the way you will do sort and MapReduce is, you will read the data, okay? You will essentially map those keys to other machines, and then you will essentially use the shuffle where you are sending the keys. Okay, so let's say you read the first key. If it's an A, you will send it to yourself because you are the node that has A through D. If it's F, you will send it to the second node or some. So you basically do that. So there's a communication phase, and then in the second stage, you receive all this information from the first stage. Then you do some local sorting, and then you write out the output. Okay? So this is how you can take a simple sorting example and convert that into a MapReduce application. Okay? And the idea is, in the map, you can essentially take any type of data processing task, and so long as you can partition it into two stages, okay? And then both stages are needed to produce the end output, you can write them in a MapReduce fashion. And what happens in the shuffle phase is, often because the amount of data is so large, you will take the intermediate output from the map, you will write it out to disk, and then the second stage will read it back from disk, do the final processing, write out the output to disk. Okay? That's how you are essentially going to write your application using MapReduce model. And there are many types of processing tasks that you can map, that you can convert into a MapReduce paradigm. Okay? This is how this platform works. It basically has a map stage and a reduce stage. Whatever data processing task you have to write it as a MapReduce application, where you have two stages, a map stage and a reduce stage. The question is?
What's the point of shuffling to, I don't know.
Yeah,
read?
question is, what is the reason to shuffle? Why can't you serialize it? You are serial, that is what you do. You say the first node is responsible for all, in the second stage responsible for all keys from A to D. This one is from E to F. But in the first stage, because you are reading an unsorted file, you will, and you are just reading the first, let's say 100 entries, you will get any arbitrary key. You have to decide who is responsible for sorting it in the second phase and have to send it to that node. Okay? So if you have node 1, you get a key with A, that's you, so you just keep it. But if you get an F, you have to then send it to the second node for the second. That's what the shuffle phase is doing. Okay? So there has to be some communication to send the second state data to the right node. Is this clear? Is this essentially MapReduce? Okay. Now there's a big data, this is a big middleware system. I just showed you the processing pipeline of it. Okay. But there are lots of other things. It has HDFS, something we had encountered when we talked about file system. That's the part, the file system part of Hadoop. That's the one that's used to store very large data sets. Okay. What are the MapReduce framework is the processing element of it. And then there are many others. There's something called Mesos, which we had encountered a while back when we were talking about distributed scheduling, if you remember. Okay, so you can essentially run MapReduce using Mesos. It will decide how many machines to give to each task. Okay? If there's large data set, maybe you need 100 nodes to process it. If it's a smaller one, you need 10. And Mesos can allocate the right amount of resources to each MapReduce task in the system. Okay? HDFS will store the data on stable intermediate output, and then there are all kinds of other things as well, which I will not discuss here, but it's a large ecosystem. Okay? Which is kind of shown here. So you have storage management, HDFS, and so on. Resource management is Yarn, which looks like Mesos, and there are data processing framework. I talked about MapReduce, I talked about Spark next, and then there are application programming languages. So you will use things like Hive and Pig to write your MapReduce code. Okay? That will then run on one of these platforms, and then they look for data from here. Okay? So it's quite complicated in terms of its overall hierarchy, but in terms of writing code, it's actually a simple framework. You can write MapReduce code using Python, for example, and it will do whatever I was talking about. Okay. So the last thing I want to say here is the Spark platform, and then we'll end. Okay. The Spark platform was essentially built to overcome a key limitation of the Hadoop or the MapReduce platform. Okay. So this was our project that came out of Berkeley, also open source. Okay. It has all kinds of things that are built on top of it. You can use it for graph processing, machine learning, streaming. You can use it for SQL. But for the moment, forget about all those upper level boxes. Let's just look at the core, which is Spark, and see what is it that it was designed for. Okay. So the key limitation of MapReduce, okay, is that it is highly I/O intensive. Okay. You are processing large data sets that are stored on disk. Okay. In the first map state, you read a lot of data. Okay. And then you produce some intermediate output, and you write that out to disk. In the second stage, you read it all back, other nodes read it, you process it, you write it back. Okay. That's how data processing works. So after each stage, you're writing to disk, reading from disk, and sending it back. Okay. Now that can slow down the processing, because as you know, disks are slow. Is something you should know. So anytime you have disk I/O, your processing speed is going to slow down. This is not like you're running something on a GPU. You will be running at the speed of disk, not at the speed of CPU or GPU, because the I/Os are going to be much slower than compute you can do on that. Okay. So the question that the designers of Spark asked is, what can we do to speed this up? Okay. Now the initial data has to be stored on disk. You can't do anything about this. Okay. So the place where you can speed up processing is the shuffle phase or the intermediate state. in Hadoop or MapReduce, you are writing that intermediate output to disk and then reading it back. They said, let's not do that. Let's keep it around in memory caches. Okay? So you take all the machines, okay, and assuming there are lots of RAM, you'll put big caches in there. Okay? So rather than writing the output of the map stage, still runs as a MapReduce program, but writing the output of map onto disk, you will write the output of that map to your cache. Okay? And then you'll try to read it back from the cache. Of course, if the cache is not big enough, you will spill to disk because you can't have infinite memory. Okay? So if that happens, you will spill to disk. But if you write your code well, you have the right number of nodes and you have the right type of intermediate output, maybe you will not spill to disk and you will have all the memory, all the data in memory. So the next phase will run much faster because reading from RAM, not reading from disk. Okay? That's the basic idea. Okay? You try to keep data in memory as much as possible and then do processing on it. Okay? So this abstraction that they created, okay, this cache that they created, you should think of it as a distributed shared memory. Okay? So it's a lot of RAM that you have across machines, you are sharing them, okay, because you can't keep all the intermediate data on your local RAM. You are essentially taking a set of memory caches and you're making them look like one large cache. So it's like a shared memory region. Okay? And they gave it a specific name which was called a RDD, okay, which is Resilient Distributed Data Set. It's basically distributed memory. Okay? And they had some interesting things here, which was if, let's say, a machine reboots, okay, whatever was in its cache is gone. Okay? You stored some intermediate output there, now the machine is restarted, okay, or just died. Now some of my intermediate data has disappeared. Okay? Now what do you do? Okay? You don't want to actually terminate the entire computation and restart from scratch because you lost some intermediate data. So you want to basically make sure that I can somehow deal with these failures. Okay? So they came up with this interesting idea, which was for every piece of data that you cache, okay, you will actually keep track of how it was produced, what computation specifically produced it. Okay? So if the machine crashed and that data disappeared, you don't actually recreate the entire computation. You just say this missing piece of data was created by these small map tasks, so I'm only going to recreate those. Okay? And you might have a chain, because it's not that Spark is limited to 2 stages like map and reduce. You can have multiple of these stages. Each stage produces an intermediate output, the next stage consumes it. So these RDDs, you track their lineage. Okay? So for every piece of data you have its lineage. So when that data disappears, you will actually just redo those computation automatically and just recreate them and put that somewhere else. Okay? That was their main idea. They did not use redundancy. You could have replicated the data. And we talked about that when we said RAID. So that is too expensive. This is main memory. Okay? You don't have enough main memory that you create 2 copies. If it was disk, you can create multiple copies. Disks are cheap. RAM is expensive. So we will not replicate, but we will recompute. Okay? But the idea is the applications don't need to do anything. If some machine dies and you need to access some RDD or some data, which is the data that was stored on it, okay, the system has tracked for every piece of object that's stored, what computation generated it, you will automatically recompute on the fly. Okay? It may take some time, because computation might take some time to run, but it will recreate. Your applications will run transparent. They might just slow down a little. Okay? So this was the big idea in Spark. They said, let's keep data in memory. Let's use the RAM on all the machines. We'll create this distributed memory, which we'll call a resilient distributed data set or an RDD. Each computation will produce some output, which will be a new data set, and that's why it's resilient. We'll keep it, but we'll track that this code generated it. So for every piece of data, I know what code to rerun to generate it, what the input was to regenerate it. And then if any failures occur, I just recompute on the fly. This essentially allowed you to do distributed data processing much faster, okay, and allowed you to use the RAM on the machines and so on. Okay. So with that I'm going to go back to this. So that's your Spark layer. Okay. Now on top of Spark, you can run other applications. You can use Spark to do ML training. Okay. The data sets just could be something you are using to train a model. Okay. So just as your PyTorch and TensorFlow, Spark is another paradigm that is used to essentially do distributed ML training. Okay, you can use many other frameworks, but this is one of them. That's their ML lipstick. Okay. They have what is called Spark streaming. If your data that's continuously coming live from some other source, you can do processing on the fly as data comes in, okay, in batch. So you can do Spark streaming. You can use Spark as a big database and run SQL queries on them. That's also supported. And you can think of this data as graphs. You can do graph Excel. There are all kinds of higher level services that sit on top of Spark. So this is actually quite popular in industry. Okay? Many cloud services also support Spark, like AWS and Azure. They will have Spark-based instances where you can run Spark jobs and so on. And on top of that, you can do all kinds of computations on that data set. Okay? So this is basically the way a lot of large-scale data processing actually occurs in the cloud today. And so I just thought you should all at least know a little bit about it. MapReduce is how it started. Spark is where it has actually ended. Okay? Any questions before we wrap up today? Yes.
So just to tie this to what we were talking about before, Spark is a type of distributed middleware? Is that
Yes.
an accurate-
Question is Spark type of distributed middleware. Both Hadoop and Spark are type of distributed middleware designed for data processing. Okay? If you think about EJBs and Corba and everything we talked about, those are designed for communication. They allow you to write applications that communicate. Here, you are trying to essentially build middleware that allows you to process large amounts of data. Yeah, that's what it is used for. But yes, it is a middleware. Anything else?
Where are, in Spark, where are those computations stored exactly?
Question is in Spark, where are the computations stored? So computations are essentially pieces of code that user writes. Okay? So what Spark will do is you will see here there's a simple graph which you may or may not be able to read that, but there is the files you create RDDs, then these black things are programs that run on the RDDs. They produce more intermediate output. Then there's another black task runs, it takes these two input, produces another output. So Spark will keep track of this graph as it's generated. For each node, it will say what code was run to produce that next stage. Okay? So this, you will know that this RDD was generated from these two RDDs using that code. Okay? Since all of this is still stored in memory, you can recreate this if you have those two. If lots of them are go away, you start from the beginning, but you only redo that path, for example. Right? So you will do the minimum computation needed to recreate all the data that's disappeared by tracking what code to rerun. That's the basic idea. Okay? Next one question.
Digression, but like where would something like Apache 9.5 fit in this ecosystem?
So there are many other middlewares we have not talked about. We didn't talk about Kafka, we didn't talk about all kinds of Apache frameworks that are built there.
Like Apache itself has like a ton of.
Apache is now a big project. You started with the web server, but there is a cloud native foundation that creates all these other kinds of things. Yes, there are many other middleware systems. It's not an exhaustive list. Right? We spent 5 minutes on talking about 10 different things, just to give you flavor of what all things are out there. But yeah, there are many more we did not cover. So you should think of them as all kinds of other systems that we have not really looked at. We didn't talk about message queuing middleware. Okay, there's things called ZeroMQ and RabbitMQ that are designed for all kinds of publish subscribe, all kinds of things we have not covered. But yes, we did do a fair bit of them already. Okay. All right, so let's end it here. One more class next Wednesday, then we are going to be done. Okay.